Good morning, good afternoon, or good evening, everyone. Thank you for joining us today and welcome to this Community Near Fault Observatory breakout session on earthquake ground motions around faults. I am Casey Adderhold, Project Associate at Incorporated Research Institutions for Seismology. IRIS is committed to fostering the exchange of scientific ideas by providing a safe, productive, and welcoming environment. All participants are expected to abide by the IRIS meeting code of conduct, which is posted in the chat. Geophysical data collected within rupture zones of significant earthquakes are essential for testing and developing further models of earthquake processes. Focusing on in situ observations in the immediate vicinity of fault zones where rocks suffer permanent deformation during faulting events could transform the understanding of earthquake physics, improve ground motion prediction estimates, and contribute to structural engineering efforts to mitigate earthquake impacts. This breakout session is one in a series of sessions intended to gather input from the broader earthquake science community on key research areas, science questions, and the data and experiments needed to address them in the near fault zone. This breakout session will be recorded and archived on the IRIS Earthquake Science Presentations YouTube channel, and the discussion held here today will inform future sessions, workshops, and proposals. Should you have a comment or question as the session unfolds, then please clearly and concisely type it into the chat box on your Zoom control panel. If you would like to ask a question or make a comment, you can also raise your hand and we'll call on you in order. At the appropriate times, we will read your name and the question to the presenters. If similar questions have been asked, we may combine or skip them. If the session happens to crash due to Zoom or internet issues, we will reboot it. Just click the Zoom link again. Automatic captions are available to be turned on and off on your Zoom control panel. I enable those right now. And to get an idea of the group we have with us today, I'm going to launch a quick poll. Please select your career stage and the type of institution you are currently employed or enrolled in, as well as your prior familiarity and interest in the Community Near Fault Observatory. This poll will remain open and we can share the results at the end of the session. I'm going to go ahead and stop sharing my screen and then pass this now to Jamie and Gail to present an introduction and moderate the rest of this session. Thank you.
Thank you, Casey. I'm not going to spend too much time talking because we want to have a lot of time for discussion. We have a few speakers lined up, and then we're going to move to a broader discussion with the whole group. I just want to emphasize some of the things that we're trying to get at in these workshops. Again, I know Casey sort of brought this up, but what are the key science questions that are not adequately answered today? What are the types of observations that we need to answer these questions? And many of you have probably seen some of the preliminary design of what a rupture fault zone rupture observatory would look like. So we want your comments, on whether we can answer these questions with an observatory that we're proposing. Another question is, what can we learn in between? If we don't have any big rupture in a 10 or 15 year period of time, what can we learn from the smaller earthquakes as the fault system is preparing for a large earthquake? And all of this is to justify the NSF support of an observatory like this. So we need answers to these questions, because obviously this is what's going to come up in any review of the observatory. So we have Ken Hudnut up first, and he's going to talk to us about what was proposed previously that was very similar to this within the USGS, and he's obviously thought about this for a long time. So I thought it would be great to get his comments on this observatory. So, Ken.
Thank you. I just emailed some slides over. I don't know if you received them and could present, or should I try?
I think Casey has them.
Pull them up. I'll pull them up right now. Sorry, just a second.
Thank you. Yeah, sorry to be last minute with the slide deck, but
no, it's
perfect. The first couple of slides give that historical background, and I just wanted to start with that. Thanks for the opportunity. What were called zipper arrays. Okay, so before I started work at USGS, there had been an effort at Parkfield to put in precisely observed small quadrilaterals along the San Andreas Fault at Parkfield, and those were under Al Lind, and my former supervisor, John Estrom, put those arrays in and surveyed them. Those were called zipper arrays, and so the idea was that in case of a Parkfield event that they would reobserve and get not only the co-seismic, but also the post-seismic deformation. And so it was even appreciated back in the early 80s, you know, and with the alignment arrays and the work that Burford and others had done, that it was important to make such observations in the near field. But that was emphasizing geodetic observations. And of course, with Superstition Hills earthquake sequence in 1987, Bob Sharp, Jim Langkemper used a steel tape to do a similar repeated observations of quadrilaterals to really quantitatively observe the afterslip. So, but then in terms of near field observations, of course, also 79, the Imperial Valley Array, those big records from near field were very influential, and same with Lucerne South from Landers, and then Pump Station 10 from Denali. And so the idea, along with the sort of the conceptual side, thinking from Heaton's slip pulse paper 1990, all of these were very influential in bringing together some thoughts that we just continued to use the term zipper array, but we extended it. So if you could maybe go to the next slide, show where our thinking was in 2007. Oh, sorry, yeah, next one. So this is part one of the slides I sent just to go over this background. So as you know, in 2007, there was an initiative, USGS got funded. It was originally scoped to be about a $100 million initiative, but I think it ended up being less than 10 million in the end. But part of it, as we were developing the ideas, was to do zipper arrays along the southern San Andreas and San Jacinto faults, as you see here, and to space them about every 10 kilometers along the fault, and to have near fault instrumentation. And the idea was to have strong motion as well as GPS. And what we got approved to do was much smaller in scale than what we had envisioned. But when I guess when Yehuda was showing the conceptual drawings for this new initiative, a bunch of people said to me, "Isn't that just like your zipper arrays?" And I think it's in part similar, but of course the instrumentation technology has evolved too. So we did get the funds to put in Southern San Andreas Fault instrumentation, and this was done prior to El Mayor Kukapa, so we got good records from that event from the new instrumentation. But what was different about it is these instruments had strong motion, single component vertical weak motion instrument, and then also GPS, all co-located. And many of these were in very remote sites. And so we felt good about what we had done there, but of course, we had wanted to do more. So this has reminded many of that prior initiative, and I just want to give that background and the name zipper array, hoping maybe that term can get repurposed and used in the future with your efforts. Next slide. Part of the idea here was that in the near field, we wanted to capture big records from big events like Southern San Andreas. If it goes off, we want to have instrumentation in place to record it. And again, from the slip pulse work by Heaton, you know, the idea being that you'd get potentially large displacements, dynamic displacements, as well as static displacements. You might get fling step, or by other names, you know, dynamic overshoot effects in the near field. But we wanted to capture and observe that so that we could go beyond theory and have actual data to then guide future modifications to, let's say, building codes. So that was the main thing I just wanted to put out there. One other further thought for consideration would be, you know, there was this whole effort with rotational ground motion observations too. Willie Lee, Evans, and others put some SRL papers together after a workshop we did. And to some extent, rotational ground motion observation has come in. I think in these near field observational observatory discussions, there should be some consideration given to 6 degree of freedom observations. In other words, it might be beneficial to not just assume that all the displacements and the near field effects are going to be X, Y, or Z, but rather you could have rotational components, and it'd be nice to observe them too. And I guess just I'd like to say, I think there could be strong benefit to consistently adding high rate GPS at this near fault instrumentation to help accurately record the ground motions and reduce as many deficiencies in the observations as possible. And I think that's my main thing. I just wanted to say briefly about some historical background on the zipper array concept and how it's evolved and how hopefully it can continue to evolve. And it seems right down the alley of what you're all trying to accomplish here. And I think probably I should limit my remarks to that for now, but in the slide deck that I sent, it has some good background on what's going on with the Southern California Edison resiliency program that I now lead. And because of that, I also know more about where Edison has property, has facilities, and where we might be able to host additional instrumentation. As you know, Edison currently hosts 50 strong motion instruments for SCSN, and we're in the process now of looking into possibly adding about 10, but that's for other purposes. That's for like ANSS priorities, CISN, and SCSN for filling in gaps in the existing network coverage. So, if we were to consider other SCE properties and whether there might be an opportunity to host some instrumentation for these new arrays, that's a possibility. I don't want to overplay that, but we could use the precedent of SCE hosting strong motion instruments at some of our substations in particular, and maybe see about doing some more of that kind of hosting. That could be beneficial. For example, we have some substations down close to the Southern San Andreas Fault. So I'll just limit my remarks to that for now.
Great, thanks, Ken.
Yeah, thank you, Ken. We want to give a question or two after each of the presenters. So if anybody has a question now that they want to ask, and in particular, Ken is not going to be here beyond 10 o'clock because he has another meeting. So it'd be good if you have a question for Ken that's pressing, ask it now, or if not, and it ends up in the chat, we can also get the answer from Ken later. So Albert, do you want to unmute and ask, or
Sure.
Do you want me to read it?
I can unmute. So Ken, thanks for the presentation. Why was the focus of the zipper arrays to be along the fault and nothing considering perpendicular to the fault?
Oh, they were they were considered to be up to like sort of the logistics of the situation. So in cases where a perpendicular array would have been possible, that was considered. There was emphasis on trying to do quadrilaterals. Just that was the thinking at the time, but I think it's generally appreciated that profile arrays could be a really good kind of configuration. We were just, doing the usual trade-offs of how many instruments could we do and how would we want to space them. And, it was more or less driven by logistical factors. Yeah, I think profile arrays would be great, actually.
Yeah, I would say that just the lack of near source stations and near source data was the other driver. And so
absolutely,
given the amount of money, we want more stations along the fault versus a bunch of stations at one spot, I think was probably the thinking back then.
That's
Frank.
That's right.
Frank has a question. Do you want to ask it, Frank?
Sure, Ken. Would you give us a little more amplification on your thoughts about the value of rotational sensors in the near field fault zone areas?
Yeah, just as a generality, I think that in the old days, the instrumentation didn't really exist to be able to capture the 6 degree of freedom observations. And much has been done in the last 10 years or so to improve the instrumentation capabilities and get the prices down on such sensors, but things like fiber optic gyros and so forth. So in the work that I did on airborne LiDAR, for example, we were using very advanced gyros along with triaxial accelerometer arrays. And so with work that I did with Craig Glennie from University of Houston and others, we were really pushing the envelope on sensor technology for inertial sensors. And so I just want to say, I think the technology has really come along, and some of that also got pushed forward as part of USGS funded efforts to improve building instrumentation. I think every place where people have tried 6 degree of freedom sensor technology, they've been finding that in free field as well as in building instrumentation that there's signal in those other components. It's not just limited to XYZ. Thanks, Frank, for a great question. But as you know from Factor and other efforts, so there's just been a lot done in that area, and the price of the sensors has come way down. So probably ought to figure out how to include those sensors.
Just as a heads up, we deployed with the University of Munich a set of or a IX Blue rotation sensor pinion flat a few weeks ago. That's streaming.
Oh, good.
Available for all. It's also embedded in a broadband array, which can be used for rotational observations also. So just it's another piece of the puzzle that's available for people to analyze.
That's great. Yeah, that's moving in the right direction. And I think the price point for some of the intermediary rotational equipment is getting there, where it was, 10 years ago or so that Millikan, there was like a $6,000 fiber optic gyro put in there. Those types of instruments are down around like under 1,000 now, I believe. So, as those prices keep dropping on really high quality equipment, please, keep those in mind, because they don't require sky view. They can be put into a vault, right, co-located with your triaxial accelerometers. Yeah.
We can talk more offline on some of this. So
yeah, I think that's great. I was just going to make a comment, and then I said, you know what, I'll just put it in the chat. And if you have comments about this, let's use the chat for that now. And so we can want to collect as many comments as possible. So please do put your comments in the chat, even if we don't, have time to have you unmute and ask the question yourself. Okay, let's move to the next presentation. Greg, are you ready?
Yes. Can you see my screen?
Perfect.
Okay. Yeah. So thank you so much for this opportunity. And with this presentation, I would like to provide a brief overview on the development of non-ergodic ground motion models and the potential ways in which the near fault data can contribute in this effort. And this presentation is based on a prior work of all the co-authors that I'm mentioning here, which has been summarized in a UCLA report. So to begin this discussion, it's an interesting way to start is to ask ourselves why we see the push towards non-ergodic ground motion models in recent years. And first of all, that happens because non-ergodic ground motion models allows us to quantify the full range of ground motion uncertainties, which is the range that the median ground motion can vary due to lack of knowledge. And once we acknowledge that, non-ergodic models provide a framework to reduce these uncertainties by collecting more data. And so in this context, non-ergodic ground motion models allow us to make best use of the available local data. As an example, when developing an ergodic ground motion model, collecting the data from one more earthquake doesn't really affect the median ground motion because it's already robust enough. However, when developing a non-ergodic ground motion model, the local data can have a huge impact as they can reduce the aforementioned ground motion uncertainties. And in my opinion, this is where this effort to collect near fault data ties in with non-ergodic ground motion models. It can help us to reduce some of these uncertainties, and in particular, those related to the systematic source effects. And from a practical point of view, non-ergodic ground motion models offer us the potential to reduce the ground motion design values, and in particular at the larger return periods. And that happens because even if we have systematic positive effects where the non-ergodic hazard curves will be shifted the right with respect to the ergodic hazard curve, due to the increase in the slope of the non-ergodic hazard curves that is introduced by the reduction of the uncertainties. At very large periods, the non-ergodic hazard curves will be below the ergodic one. So as we are all familiar, ground motion models are nothing more than a simple statistical model whose goal is to describe the effects related to the source, path, and site that control the ground motion. And it does that, and it achieves that by using simple parameters as proxies, such as magnitude, style of folding, and rupture distance, to quantify effects like the energy release, the seismic energy release at the fault, anelastic attenuation, scattering, and so on. But as with any model, it's not a perfect model that can explain everything. And so the misfit between a ground motion observation and the median prediction of the ground motion using a ground motion model is what we describe as aleatory variability. And in ground motion model practice, this is typically quantified in terms of a between event and within event aleatory term that we can see here. The between event term is the average shift of the ground motion for a particular earthquake with respect to the median ground motion, whereas the within event term describes the variability of the ground motion for a single earthquake. So it's worth taking a step back and really asking ourselves, what are the sources that are contributing to this misfit? And the obvious one is the true randomness in the earthquake process. So which, no matter how many data we can collect, we will never be able to predict for future earthquakes. And one example is the stress distribution on a fault and how that controls the ground motion for future earthquakes. But another source that leads to misfit in ground motion model has to do with the model simplifications. For example, in ground motion models, we use the VS30 as a parameter to describe the site amplification, but we know that site amplification is a much more complex phenomenon that depends on the entire velocity profile. And this is where ergodic and non-ergodic ground motion models are different. In non-ergodic ground motion models, the goal is to distinguish these two sources of misfit and treat them separately, because for the second source of misfit, as we collect more data, we can refine our estimates and improve the accuracy of our predictions. And again, to tie it to this project, this is where collecting near fault data will be helpful, as it will help us to better understand and reduce the simplifications that has to do with the source modeling. In non-ergodic models, the systematic effects are grouped in three main categories. Those that are related to the source effects, and those can be systematic differences in the ground motion due to differences in the median stress drop between neighboring faults, systematic effects that are related to the path, and those may have to do with differences in the anelastic attenuation at different parts of the crust, and systematic differences in the site effects that has to do with the differences in site amplification between our site-specific velocity profile and the average velocity profile for the same VS30 value. But what is important to recognize is that there is no loss or gain of information. The difference is how the same information is treated. So in ergodic models, everything is treated as random, that cannot be predicted for future events, whereas in non-ergodic models, we separate them into the epistemic terms, which as we collect more data, we can better refine and estimate more accurately, and the remaining aleatory term, which what we cannot learn for future earthquakes. And the same is true for the standard deviation terms. So the full amount of aleatory variability in ergodic model is equal to the epistemic uncertainty of the non-ergodic model before we have any local data available, and the remaining aleatory variability. And so in practice, the way that we are formulating a non-ergodic model is by starting with an ergodic base model to capture the average scaling relationships, which realistically we cannot estimate using just the available data, and also incorporate some of the constraints that we want in order to ensure proper extrapolation outside the range of interest, such as the short distance magnitude saturation. And then we introduce some spatially varying coefficient to capture the systematic effects related to the source and site. And this figure shows an example of how these systematic effect, these spatially varying coefficients can vary in our domain of interest, which is in case is California, and the cell-specific and elastic attenuation, which is an approach that we use to describe the systematic path effects. In this case, we discretize our domain of interest into individual cells, and the total and elastic attenuation that is experienced at our site would be, and each of these, in this approach, we take our domain of interest and we discretize it into cells, and we assume that each of these cells have their own anelastic attenuation coefficient. And so the total anelastic attenuation that is experienced at our site will be equal to the anelastic attenuation of all the cells that are crossed by the path that connects the closest point on the rupture to the site. And so in this approach, the areas where the near fault data would be most useful are in having more data to describe and estimate the systematic effects that are related to the source, but also in help us reevaluate some of the constraints that we used when developed the ergodic models, such as the magnitude saturation at short distances. And an example that shows the differences between ergodic and non-ergodic models can be seen in this slide. So at the top line, we have an earthquake that is located in Bay Area, while in the bottom line, we have an earthquake, in the bottom row, we have an earthquake that is located in Los Angeles. And as we can see, in the prediction of an ergodic model, the location of the earthquake is not important. So we will have the same attenuation whether the earthquake is in Bay Area or in Los Angeles. However, for the non-ergodic models, the location of the earthquake and the site matters, because that will dictate the influence of the systematic effects. So we can see a different distance scaling between the two regions. But what is important also is to remember that there are two components in the non-ergodic models. We have the median, we have the change to the median ground motion, but we also have the epistemic uncertainty. And we can see that in non-ergodic models, in areas where we have a lot of data, the epistemic uncertainty is small, whereas in areas where we don't have any data, the epistemic uncertainty is larger. And this is another area where this project is going to provide major contributions, as it will provide more stations, and in areas where we previously didn't have any available data, to further reduce the epistemic uncertainties. And we can see the impact of all of this in the seismic hazard in this slide. Starting with an ergodic model, we get a single hazard curve that is shown with a black line. And now if we change to a non-ergodic model, we will have multiple hazard curves showing the full range of epistemic uncertainty. And as we collect more data, we can reject some of the alternative branches and reduce the range of uncertainties. So in the figure on the left, we can see a case where the available local data told us that the systematic effects are negative, meaning that on average, we would expect ground motions at our site to be less than the average ground motions. And that's why we see this offset between the orange and the black line. Whereas in the figure on the right, we have a case where the available data indicate that the systematic effects are positive, meaning that on average, the ground motions will be larger than the average ground motion for the same type of earthquake. But what we can observe is that due to the increase in the slope at the large return periods, for the same annual hazard, the non-ergodic ground motion is going to be less than the ergodic value. And in conclusion, to tie it to the questions that were asked to address, the key questions that can be answered using small and moderate earthquakes with this new set of data would be to better understand and model the different components of the non-ergodic effects, and in particular to separate the systematic source and path effects. That's because if we only have stations that are at moderate or large distances, we would see the combined effect of the source and the path. Whereas if we have also stations that are closer to the source, then it would be easier to separate the impact of the source effects from the impact of the path effects. It can also help us to relate the systematic source effect to physical processes. And that's important because in that case, these non-ergodic effects that I have been describing will not just be the product of a statistical model, but they will be tied to some real phenomena. And as an example, it was mentioned that this type of data can help us to better estimate the dynamic and static stress drop. So there can be an effort to test whether such parameters are correlate with the non-ergodic source effect that we have been observing. And these data can also help us to study other near fault effects, such as the radiation patterns and directivity effects. Now, in a longer time scale, with large earthquakes, this data can help us to better understand and maybe refine some of the constraints that are used in ground motion models, ergodic and non-ergodic. For example, one such case would be the magnitude saturation at short distances that currently is forced to have zero saturation because we don't have enough data to really know how they really behave. And another question that they can help us answer is to test whether the systematic source effects that we observe from the small earthquakes can be used to predict the systematic effects of large events. And on a slightly different topic, not related to ground motion models, but related to fault displacement models, these types of data can also be used to study if there is any correlation between the near field ground motion and permanent tectonic displacement. And that can be important for infrastructure that is crossing active faults, and so it's susceptible to permanent displacement, but it's also sensitive to ground motions. In terms of the areas that this data could contribute, I believe this set of data will fill the gap in the current empirical data sets, as right now we don't have so many observations at distances less to 10 kilometers. And so they can be used to validate both numerical models and empirical ground motion models for near fault effects. And in terms of the configuration of these arrays, I think the denser, the better. But if I was to provide some dimensions, I think it would be really useful if it's less than the order of tens of kilometers. So in one to like 5 kilometers, where we can really study and see if we can observe the fine spatial variation of the ground motion. And that concludes my presentation. So thank you very much.
Thank you, Greg. Let's open it up for a couple of questions from the group. I don't see anything in the chat, I don't think.
I have one quick one then while others are waiting in. Thanks, Greg. I'm interested in the sort of the cells that you have for attenuation, and you're looking at those primarily right now in terms of an inelastic factor varying. Have you thought about the implications of maybe making that cellular attenuation more broad, including differences in velocity structure and so on that might affect apparent geometric spreading effects, and possibly tying that cellular attenuation in with simulation-based predictions?
Yeah, both of these are really good questions. With respect to the first one, yes, we are currently going through an effort to see how we can also model the systematic effects that we see in geometrical spreading, and this may be formulated in a way similar to the cells or as a spatially varying coefficients, but this is something that we are currently studying. And for the tying it to numerical simulations would be certainly very useful. Qualitatively, we see some correlation between the inelastic attenuation, the spatial patterns on the attenuation cells and Q models. So I think we should also try to more quantitatively try to correlate these two parameters and see if numerical simulations can help us to inform some of the non-ergodic path effects.
Thanks.
Bob, you want to unmute and ask your question?
Yep. So I just want to follow up on the last recommendation that you had, which was suggesting that the sort of observations most useful to you are on the 3 to 5 kilometer sort of station spacing. But I think what we're proposing is groups of strong motion stations located very close together within, say, 100, 200 meters. And then those groups are separated by distances of 30 kilometers. Can you, I guess what I'm mostly interested in is, are you suggesting it's more useful to have singular stations at spacings of 5 or 10 kilometers versus this kind of tight grouping? Because I would think that, I'm not sure the 4 or 6 stations that are very close together will actually measure the same thing. And that might be interesting for some of your modeling.
Yeah, that's a difficult question to answer because we don't know how these data are going to look like, but definitely having these groups of stations will be helpful to see if there are differences. But what I was mainly referring was the other dimension, the dimension along the fault. And I was thinking that if it's possible, the closer the spacing between those groups of stations are, I think it will also be informative in understanding how the ground motion can change along the fault.
I would comment that, I would follow up with Bob. I mean, some of the nodal things that we've run on the Santa Sona fault show a high degree of variability, even at 10, 20, 30 meter interstation spacing. So there's a strong reason to make, I mean, understanding what happens at different sections of the faults is very important, but also an understanding of much tighter spacing seems to be a highly variable and not well understood problem yet.
Yeah, I think the tighter spacing will be useful for slightly different questions like the spatial coherency of ground motions.
Right.
Just
Okay,
jumping in, I think
Oh, go ahead,
on
Albert.
the relationship between spatial coverage and density, like ideally we would have dense stations everywhere, right? But I think that the combination of distributed dense locations would be used to inform both sort of the path effects that Greg is talking about, but also local effects and local correlation structures that are important too. So I think it's a balance about just trying to make it efficient and answer as many questions as you can, right?
Right. And also keep in mind the relationship of these stations that are going in with all of the other existing stations. This array isn't going to be operating in a vacuum.
Exactly.
Okay, let's, if people have additional comments, please get them in the chat and let's move on. I think Norm is up next.
And I can just share my screen. Is that all right? Is that working?
Yep, it's working.
So this will be short. Related to what Greg just presented, we really are focused on ground motion models on moving to non-ergodic, and this is what has to be done really to make progress. The key of all this is when we're doing that, we're mainly using small magnitude data. So the plot on the right just shows the data set we've been using for non-ergodic models in California. You can see the bulk of the data are below magnitude 5, right? Because that gives us enough data or samples to see things spatially and how they're varying. And then we only use these effects on things that we think are linear behavior in the crust, like the path effects and linear site terms. And the source becomes a more questionable problem. Is the source really linear? But we have to make that assumption to be able to extrapolate these effects from small magnitudes to large magnitudes. Greg talked about the non-ergodic path effects. That's the biggest piece of reducing the aleatory variability in the ground motion model. It goes path effects are right now the biggest. Next is site terms, and then the next is the source terms in at least the simple way we're modeling things. But these path effects using the cells mainly pick up effects of Q, right? That's what it's mimicking. So that shows up at large distances and for short periods. But we need things that work at short distances that are most important for hazard. Okay, so moving those path effects to shorter distances is an issue. And we see non-ergodic or spatial variations in the source effects or source terms from small magnitudes. So you can see one part of the state is higher than another part of the state. That can be in the simplest way attributed to, let's say, the median stress drop in an area, if you think about it. But our main question is, we have all this from small magnitudes, does this tell us anything about large magnitudes? So how do you, if I've got lower than average ground motions from magnitude 4s from a region, does that mean lower than average magnitude 7s, or are they just completely independent? So in our non-ergodic models right now, we usually run them in two cases. One where you could assume the source effects from the small magnitudes are applicable to bigger ones, and others where we throw them out and say, no, those just aren't informative. So that's going to be a fundamental science question for us. Can we get information on the behavior of the large magnitude events, knowing the variations in the source behavior for small magnitudes? When we're doing, the other key is, ground motion models are moving to a mixture of incorporating 3D simulations and empirical data. The parameters that we have in the 3D simulations for the source that are used for large magnitudes are essentially, these are calibrated by the same sparse data that we have to make the ground motion models, right? So we don't have that many large magnitude events to work with. And so we're calibrating them to the same data. So they're really not independent estimates. You know, the 3D simulation calibrated to ground motion data and a ground motion model calibrated to that same ground motion data and using the simulations to constrain the extrapolation have a tremendous overlap, right? And so the idea is really to get something better to help constrain these source parameters from large magnitude events. And so, but this is back to waiting decades, right? To capture these kinds of events and have them really well sampled along strike so that you can see what's happening on different parts of the rupture. The other part, so this is back to when you put out these arrays, these are decades long things. This isn't as something you want to stop after 5 or 10 years. And then the other part is really pushing these simulations, in particular, non-ergodic for us means 3D simulations, and pushing them to higher frequencies. And there's been a lot of effort towards that right now, getting the calculations to run up to higher frequencies like 5 hertz. But it all comes down to, do you know the 3D crustal structure accurate to really justify that kind of a simulation? So currently the models will put in a stochastic velocity structure at high frequencies, which really isn't what we're after for trying to get at truly what is the behavior. And so this really needs getting better characterization. So as long as when you're putting out this array, there has to be in parallel a geophysical studies to really give us the characterization, not only of the large scale features, but getting at the things that affect the shorter wavelengths or higher frequencies. While waiting, so we'll assume lots of small magnitude data, and what can we do for all of that? So it's really getting at path effects for short distances. And Gail sort of alluded to that in asking when we're doing the cells approach on non-ergodic, that's Q, which shows up at large distances. But what about the effects of the 3D velocity structure at short distances that we really care about? And in particular, what's shown on how spatial variable are these short distance pathoterms, and can we really start to get at these at less than, say, 15 kilometers? And the plot on the right is just related to how to deal with high frequency ground motions. These dashed lines are the ASK14 ground motion model for magnitude 4 at different spectral periods, 1 second PJ and then 0.2 hertz or 0.2 seconds. And then the solid lines are what's come out of looking at the induced earthquake data, where you have recordings at shorter distances. And we get a much steeper slope. And Gail's talked about this for years, but it's now sinking down to the rest of us that we have to put in a steep slope in this first part of the attenuation from these moderate magnitudes. And if you're not going to model a big earthquake as a sum of a whole bunch of small ones, are we really capturing this high frequency rapid attenuation in the first 10 kilometers? And how stable is that? Because currently we're effectively using ergodic models saying everywhere has the same slope. Is it going to be very different for different regions or not? And so as you go up and down the San Andreas even, what kind of scale you want to get at? To get at these types of effects here, you talked about distances. We need recordings pretty dense. If I go back to this first plot, you will see we actually have more data at small distances from big earthquakes than we do from the little ones. And the reason is a big earthquake has a larger rupture, so there's a better chance that you have a station located at a short distance away. Whereas to get a short distance for these small ones, you have to be, have put your instrument right over the over it, or it needs to have ruptured to a shallow depth to try to get these shorter distances. So trying to find out what's happening at short distances, I think, is a key. And just to answer Gail's question, this is to do the path effects from the 3D structure, you need to have two parts of the path term, a Q term, that's our linear R. And then you could think of this as geometrical spreading. We're not modeling this as geometrical spreading. We're actually modeling it as a path term from a site to a particular location. So this is a plot of the sources here. Then we get higher than average ground motions, but this isn't a geometrical spreading all in one direction. For example, here it goes down and then it goes back up again, right? So our attenuation starts to look like what's plotted by the red curves as opposed to our smooth curves. And so you can do this. Here we had very dense data from 3D simulations from Cybershake, but you would need to have recordings, spacing 10 kilometers isn't going to do it. It's got to be, several kilometers, maybe 2 or 3 kilometers between stations, not 10 kilometers to really get at what are these path effects at the short periods that we're after. All right, and that's all I have. Thank you.
Thanks, Norm. Questions?
That's great. Thanks, Norm.
So I'll ask a question, Norm. What about the near fault? Sorry. I mean, right now we're just focused on surface sensors in your work. Are there other types of instrumentation that would be valuable to answer some of these questions? Or?
Well, what I think having all of this data at the surface is only going to be really valuable if you have detailed geophysical and geology studies at depth, right? So that you can interpret it. So those two things have to go together. So to me, that's, boreholes are nice, but I would rather have a detailed velocity structure that you can use to help guide the interpretation of what these data are, because they're going to be highly variable. And if you don't know what's down underneath the surface, you can't interpret what's causing that variability.
That it does raise a really good question, though, about what the possible contribution to, of boreholes would be. Obviously, in an ideal world, we would have both the observations at the surface and ones below the sediment layer in a borehole.
Yeah. At multiple depths, right? All the way down to a kilometer. But,
well, you don't want much.
No. Some boreholes may, the question is scope. In the US, we have tended to go for lots on the surface and fewer boreholes. If you go to Japan, it's the opposite, right? They want boreholes and fewer on the surface. So I'm probably influenced by that decades of let's get lots of recordings at the surface.
Right.
But as I said, it's really difficult to interpret them without knowing something about what's going on at depth.
Yeah, and I think you can. Oh, boreholes can be. People can have false confidence in what a borehole is actually telling you, because the wave field is very complex down there.
Yeah.
Right.
Yeah. It may be that where you might consider putting boreholes in is partly dependent on the subsurface structure, in that, to me, it's really useful if you can have a borehole instrument that is actually at, the rock level. Just putting a borehole down, 10 meters or 20 meters into soil that is 100 meters deep, to me, isn't as useful. But if you have sites where there's a solid bedrock at a reasonable depth, that might be the place to consider putting in a borehole instrument as well.
But I'll just say that boreholes are really expensive. We just have some recent experience in trying to add a borehole to the Harvard Observatory or the GSN station. the USGS research drilling team has spent 3 weeks drilling 200-meter holes. So they're trying to keep them vertical, but it's just an expensive, uncertain process.
Right. But
We got
100
a
meters
hand
may be too
raised.
deep.
Tara, do you want to ask your question?
Oh, hi. Yes, I did have a question, but it was different than the borehole topic. So if you guys have more to say about that, I can ask my question.
No, go ahead. We need to move forward. So this will be the last question and then we'll move on. Go
Okay.
ahead.
Hi, first of all, I really enjoyed your presentation. Norm, I'm a graduate student, so my question's a lot more basic, but it was just about what you'd said at the end, about how we're interested with the path effects on 2D Q structure and 3D velocity structure. And I was just curious, like, why 2D for one versus 3D for the other?
Because it's where you can, I think, capture most of the effects of the Q structure in 2D, because it's mainly, since we multiply that by R, by the linear distance, it doesn't really show up until you're at larger distances away. Whereas for the velocity structure, it has to be 3D to pick up all of the wave bending and things like that. So I think you can get most of the bulk of the Q effects with the 2D model, but you need a 3D model for the velocity structure. You can do 3D Q, but I don't think it's going to add as much as the extra effort it will cost.
Okay, yeah, that makes sense. Thank you.
Okay. Let's see. Who is up next? Annemarie.
All right, great. Let's see. Is that working?
Yes.
You guys see the slides? Okay, I'm never sure. So yeah, it was really nice talks by Greg and Norm. And I think I agree with a lot of the stuff that they said. And I'll just show a little bit from a different perspective, just some sort of observation. So as smattering, so a couple of results from various studies, just to highlight what we can do and the need for near fault and near source observations. Let's see. Okay, so first example, this is work that I did with Valerie, or that Valerie Sahakian did really, using small magnitude data in ANZA. And I just want to highlight, you all asked a question about what we can do with the small magnitude data. So this is a good example. So these are the data set of magnitude 1 through 4 earthquakes. So real briefly, the map on the left and the magnitude versus distance plot, Valerie created a regional small magnitude ground motion and then decomposed that into path terms. And on the right was just a schematic we kind of drew up about how we might think about correlating the velocity model with the path residuals. So this was just a smaller subset of the data as a schematic, really. The colored lines show that path residual, the path term, overlaid on a velocity model. But Valerie did a much more thorough study. So for every event station path, she ray traced through the 3D velocity model. So just what Norm was talking about. On the right is showing that sort of 3D representation of what those paths actually look like when you ray trace through them. And they're colored by the observed ground motion path residual. And then on the bottom here is showing the correlation of the actual path residual on the y-axis, so the observed ground motion path residual, and on the x-axis is that velocity, the gradient of the velocity model along those ray traced paths. So you can see there's a correlation there. When you have a larger gradient of velocity, you decrease the path terms. So we saw that there is definitely a correlation with the 3D velocity model and the observed ground motion residuals. I will say that we only saw this correlation at longer path lengths. I think that's in part due to the resolution of the velocity model, and perhaps a finer scale velocity model will be able to show these gradients, right? So it's a difference in the velocity model blocks. So I think this is a promising thing that could be done at a smaller sort of resolution. We also saw here, though, that there was no magnitude dependence, at least within the magnitude range we looked at. So I think there is promise, again, to scale that up to larger events. And I'll just point out that, even though we saw these at longer path distances, we still want those fault crossing paths. So having those stations near the fault, especially, in Southern California, where we can go from one fault to another. So I think even increasing the density near the fault would help even at these longer distances. The second study I was going to highlight quickly was work done by Chris Johnson and Debbie Kilb and Frank Vernon, looking at sagebrush flats. So again, this is another small magnitude data set, magnitudes 2 to 4. It's showing 38 events that were recorded at the nodal array. And on the left, we're looking at the site effects now from PGV data. And you can pretty clearly in that top plot just see that there are small scale basins that are highlighted. And obviously you wouldn't be able to see this if you didn't have this density of stations. And then the bottom plot on the left is showing the, I think it should be VSS, the variability of those site response. And you can see again that there is spatial correlation, even on this really small length scale. And again, you just wouldn't be able to see that without this dense network. The right is similar, just showing the site response from 2 specific earthquakes, one coming from the north on the top and one coming from the south on the bottom. And again, you can see kind of similar patterns where we're able to highlight the basins there. Moving north, this is just an example from the 2014 magnitude 6 South Napa earthquake, which I don't know if you can see the cursor, but the event started here. This is a map of the PSA 1 second residuals to the ground motion model. And there's a hint here, maybe that you can see fault guided or fault zone trapped waves coming south from the Napa fault onto these faults in the East Bay, and maybe that indicates some fault connectivity through here. But at this sort of resolution of the stations, it's really hard to say. So again, if we had denser stations along these faults, I think we would be able to sort of answer these questions more definitively. So there's a lot of question marks in my slide here as to that's indeed what we are seeing, or if these are other effects. And I think in this particular case, Rufus Catchings and others also saw similar results when they deployed denser instruments and caught aftershocks. But it would be great, to have denser arrays along these faults to answer these questions. Here's an example from Grace Parker looking at the Ridgecrest events. And this is looking a little bit more at source. So these are aftershocks of magnitude 4.5 or larger. So again, some smaller magnitude data. On the right-hand side is PGA and 5 seconds PSA, where the colored dots are the event terms from those aftershocks. And so, we kind of have this question, do we see some spatial pattern of how the aftershock event terms are distributed along the main shock fault planes? So the 7.1 here and even along the 6.4. But I think really to answer these questions, we still, again, need to be able to better constrain the event terms near fault and have a higher density of instruments. This is the same idea, but just flipping the view, again, looking at the PGA and PSA 5 second, and now looking at a depth slice along strike of the magnitude 7.1. And this was done pretty early after the event, but this was a main shock fault slip contours from Gavin Hayes, shown in the colored contours. And again, just we had this question, is there something we can say about the energy, the event terms, source parameters from the aftershocks in relation to what happened on the main shock fault plane? I think it's kind of inconclusive at this scale. So I think, having that increased data would help. And this sort of segues into maybe I think it's tomorrow actually, breakout session that Daniel and others and Ahmed are running about sort of source parameters. So we're continuing to look at this particular question through our stress drop validation tag, which is focused on the Ridgecrest event. And here this was magnitude 4.5 aftershocks and larger. We can go down to much smaller aftershocks with now in that data set. And lastly, from Grace's work, again, with the Ridgecrest events, the magnitude 6.4 on the left and 7.1 on the right, trying to pull out the source and the path components to look for directivity. And so with the network stations, here's the 6.4, you can see sort of amplified ground motions in this direction. And then for the 7.1, you can see generally de-amplified directions, ground motions in this direction. But again, at this resolution with this station set, it's hard to say if that's definitive. Yet this is what we have shortly after a large earthquake to work with. I think this is my last bit, just sort of getting a little bit in towards what Greg was talking about with the non-ergodic ground motions. Again, this is the example from South Napa on the left. And here you can see that the near source ground motions were really well modeled by the ground motion model, which I would interpret as having, average event term, having an average stress drop. And that tells us something about the source of the earthquake. But there's more attenuation in this region, which pulls, the average event term or the ground motion bias term down. So unless you're carefully separating the source and the path terms, which I think, Greg is certainly doing in the non-ergodic models, then you can misinterpret the ground motion data. So either the geometric spreading or the Q. And on the right is just a more generalized example where when you look at the event terms or the source terms from the close-in data, that's the blue and the green, the blue circles and the green triangles. You do see that there is a trade-off in how you're fitting the geometric spreading or the Q with the event term. But if you consider that the event term is averaged over all of the records, then you're unable to see that sort of incorrect path information. So again, here we just need the, it's been said several times, but we just need the near source ground motion data to be able to constrain this information. So without that near source ground motion information, you also can't constrain the path. Oh, sorry, I had one more. I can't resist adding in a little bit more about stress drop. This is just looking at the stress drop modeled from area intensity ground motion and just demonstrating that we see these unique patterns of how the stress drop is decreasing under this metric when you get close to the fault. So here's 10 kilometers, 1 kilometer, and we do have a couple records of large events here, and this is because we're seeing near source saturation and due to finite fault effects. But we have very few records, in fact, no records in this region for the small earthquakes, the purple earthquakes. So more close-in records would enable us to sort of again better understand the source effects that are going on here from the ground motion. So I'll leave it there, I guess, and if there's any questions.
Thanks, Annemarie. So there's a couple questions in the chat. Annemarie, do you want to unmute and ask your question?
Yeah, sure. Actually, that was a general question to everyone, not specific to Annemarie's presentation. By the way, it was a great presentation. Thank you so much. So I was wondering, at what capacity can we use these near fault observations and the findings from these studies in the West Coast to improve the hazard estimates in the other data poor regions? And what would be transferable and what would not be transferable to other regions? And also is there anything we can do at planning stage for data collection or array design that would help such efforts, just thinking ahead of steps to just a few steps ahead for expansion of such knowledge to other regions? Yeah, thank you.
I guess one thing I can say quickly, and I can let other folks answer as well, is that in the work that Valerie Sahakian did, we saw that we can just use a velocity model to understand the path terms, right? And so we can have non-seismic velocity models, geology-based velocity models. And so then we can develop these methods where we do have seismicity, right, to validate the methods and apply them other places where we have, less seismicity, but we still have some geologic understanding.
So are you saying that if we can have the correlations established from these studies with the geological information or velocity information versus these pad effects, then we can, if such information is available and at the other target regions, we can implement those? I think
I think that's RID here. And obviously you can do this similar kind of thing and run simulations as well. But yeah, then you don't need as much seismicity, right, in other regions.
Yeah, good point. Thank you.
Can I add to that, Annemarie, that
Yeah, of course.
a couple things that we get out of this is, one is, what is the size of the effect and the spatial correlation? And we are taking these spatial correlations and moving them to other areas to say, is that a sort of a generic number? At least that's a starting point for that. It really tells you how much you can improve things, right? And starts to give you a quantitative basis for saying, if you go do this elsewhere and start to collect this information, here's how much you can improve your estimate, really justifying the need for enhanced instrumentation and recordings in more of the urban areas, right? So that we can improve the hazard. The other thing is that, given a detailed physical model and your observations, how good is your physical model, right? So it gives you some estimate of the uncertainty that even if you go to your new area and you build your 3D velocity structure, what kind of error are you going to get in that? And that has to happen. We need some way to quantify accuracy of numerical simulations. And we can take that number and say, I'm going to take this uncertainty from this area here where we've studied in detail, and say, wherever I go and build a 3D velocity model, it's going to have, that same level of uncertainty going forward. I think there's a lot of uses here that can be transported, not just in California, but actually these things get used around the world very quickly.
Yeah, that wasn't. Yeah, thank you very much for the explanation. My question was like not as a critic, but as something to think about. And thank you for the clarification, Norm.
Okay, just looking at the time, so let's move on to the last speaker here today, Albert.
Okay, so I threw this together last night, so it doesn't have quite as many figures as everyone else, but hopefully it'll be beneficial. And this is my title that I came up to after the end of that. Next slide, please. So I presented this. I just went through the questions that were asked and provided some answers. I saw Norm's presentation and Greg's, and so I knew that ground motion was going to be talked about. And I think that this is, a really important topic. Having data within 10 kilometers is so rare. But there's a lot of facilities that are within 10 kilometers. And so we have of faults, and the question of what is the ground motion at those locations is a big uncertainty. And that's been identified. The other questions I think the earthquake cycle is poorly understood, especially from a hazard perspective and how we model that. And I show up the classic tombstone plot of earthquakes in the Bay Area. And when are we going to start entering in a period where we had regular magnitude 5s and 6 in the region? We're not there yet. Everyone gets excited about a magnitude 5.1. So what is it going to take? How does that progress of the fault system go to being dormant, to being active, and how does the switching on work? And how can we model this change? I think is a really fundamental question that hopefully the types of observations that are going to be collected with these near fault arrays can help answer. More specifically, and I think about one of the questions I have is, how does the relationship of fault plane geometry and complexity of the fault influence ground motion? And if we have ruptures on very simple fault planes, planar faults versus very complicated ruptures, do we see a stronger or weaker motion? And can we use these detailed observations to help get at that behavior? And even more specifically, dynamic rupture simulations have shown the importance of plastic zones for capturing fault displacement near the surface. But there's really not any data to calibrate the characteristics of those zones, their width and their behavior. And so we need more information collected in detail from these types of observations to really help constrain that. Okay, Next slide, please. So what observations are required? You know, I think we can, the challenge is going to be we need strong shaking, and magnitude 5 is not really even that strong. So ideally we would want something at 6 and 7 that's going to break the surface, that's really going to provide us with information. And the problem is these are really unlikely to occur. And so we either can use time or space to help fill in and make sure that we're able to record some large events with such a project. And so I think first, like, we're going to have long-term support for the project. And I think, I don't know how that happens, but you know, I think we need to be thinking of 10 to 20 years time frame at least, so that we can really make sure we're going to be able to record a large event eventually. We also want to instrument multiple fault locations, maybe multiple faults, so that we can really spread out, put our eggs in lots of baskets, so that we can eventually record that large event. And I think it's probably more valuable to record a large event than to have a really detailed understanding of lots of small events. But that's sort of the balance. And I guess the question is, you know, is there any tools that we can use now to identify fault sections that we think are more or less likely? And I know there's all sorts of challenges with trying to predict this, but is there anything that we can do in science now that can help us, even if it's uncertain? I think that would be a good question. We've talked a little bit in terms of spacing, and I think the spacing is a challenge between how many areas you want to cover and scale and all of that. We didn't really talk about very many other sensor technologies other than basically recording ground shaking and maybe rotation. So that's not really what I work in, but I just want to make sure that we're recording high enough frequency, and thinking about supplementing density with temporary deployments to improve velocity models. Because as Norm pointed out, really understanding the structure of what's beneath our sensors is going to be really important. And we can do some of that with the sensors that are out there, but we can actually, if we put in high velocity temporary deployments, we can maybe help offset that. Next slide. What will we learn prior to a large rupture? So I think the small events are going to be really helpful for developing detailed velocity models. We've talked about the path and models that Greg would be interested in developing. And with more detailed velocity models, first we can understand the phenomenon of the wave propagation process, but we can also use those velocity models to help inform the location of events that are occurring at depth. And once we understand the location of those events, we can better understand how the events are migrating as the rupture cycle advances, and maybe help understand sort of the process of how the fault is developing with time, to understand sort of the physics of the fault rupture cycle. I also think that one of the big questions in geotechnical engineering is near surface damping, and how do we model that? We typically struggle with making measurements of it in the field because we don't have enough energy sources that are and separating the different types of wave effects that are associated with damping. And so I think some of these dense arrays might be able to help us inform on that, which would be helpful. Next slide. I didn't have anything for this, because I think that it's just the biggest thing is how does just have to make sure they're out long enough so we can capture those large earthquakes or that large earthquake that'll occur. Next slide, please. And next slide again. So how does this advance the next generation? So first of all, if the project's successful, then it needs to exist for a long time and have good spatial coverage. And it's something that we need to start now so that we can do the weighting. Because if we put off the weighting to the next generation, they're going to be doing the weighting game instead of us. I think that such near fault observations, without such an observatory, that near fault observations will only be captured in the rare exception. Norm showed the figure of we have some data from large events, but very little from small events. And so we're never going to gain that data if we don't put in the instrumentation. And without any observational data, we don't have any ability to do science. We don't have any observations that we can test our hypotheses and refine our understanding. And so I think this is a really fundamental question that needs support to be answered. But my biggest worry, and this is a worry of any time you put out instrumentation, is making sure the instrumentation is around for the events that are really going to be valuable. So yeah, that's it.
Thank you, Albert. Yeah, and thank you for really going at those questions. That was.
I was like, I think this is what I'm supposed to do.
Yeah, no. That's exactly kind of what we wanted to get at. So, comments, questions from others. Bob?
I'd just like to address the duration of the observation period, or how we get at the length of the project. Right now, the plan would be to utilize NSF funding to leverage scientific insight and planning and purchasing the instrumentation, get the array going, and that could last up to about 7 or 8 years, that process of getting it operating. The ongoing operation is estimated to cost about $3 million a year, and we think that could be sustained through either state or USGS type of funding, but that's a new effort that would have to be built up. That promise can't happen until the first, establishing the array or the observatory, whatever you want to call it, gets on solid footing with somebody, and then you can work on the next step. So it's a two-part chicken and egg type of problem, but I don't think it's all that impossible to get the funding for ongoing observations for another 20 years if it's designed to be efficient and operate well in that out year time frame. It's not a $10 or $20 million a year type of project. It's around 3.
Oh, the one other point I wanted to point out on the funding, or on the spatial coverage, is I think it's really good to think about large scale spatial distribution to talk about, so that any insights that we're gaining, they're not specific to that area, but rather what's the difference between specific to that fault system and maybe more general trends. And if you put in a really detailed array in one location, you might have, or on one fault system, you might interpret that fault system to be characteristic of all fault systems, and that may not be the case. So sort of, if we look too microscopic, we won't see the larger picture, and we might be our world might be distorted from that. And then on the funding and the $3 million, like in the past, like administrations come and go. Is there any way to put in like some sort of endowment or long-term funding or some sort of pool of money that can be filled up and used over time, so that you can actually have more longevity? Or
Yeah, an endowment is a possibility, but there are few government agencies that will allow you to bank money. They want the authority to administer their funds on a year-by-year basis or over short 3 to 5 year type of timeframes, and they won't let you do that.
yeah, maybe we need to think about going after some wealthy donors to support earthquake science. The other thing, Albert, is there's some trade-off between the scale, the spatial scale, and the logistics of the operations. The bigger the scale, the harder those logistics are. Not that it can't be done, but yeah, and then, you know, right now we have a proposal that looks at 3 faults, the San Andreas, the San Jacinto, and the Elsinore, and pretty much it's limited to Southern California, but that's not to say it couldn't get expanded. It's just we have to think about, you know, how are we stretching the resources and the logistics of doing that. But I agree that having just one fault is definitely not ideal.
In terms of generalizing, you know, to other regions and broadening, it's useful to also remember that there are other projects. You know, we've recently heard a little bit about the Near Fault Observatory in Europe, and so if this becomes part of a more international network of loosely affiliated near fault observatories, there would be more potential to leverage the knowledge more broadly. I think we have probably just a few minutes left at this point. So maybe I think we've had a lot of the general discussion has taken place quite naturally during the course of the excellent presentations that we've had today. In the last few minutes, maybe we can just open the floor for any other general comments on the discussion questions that have been raised.
Art, you have your hand up. You're mute. We can't hear you. It doesn't look like you're muted. You're muted, but
It must be, I think your audio might not be connected to the right setting. Still can't hear you.
maybe Art, maybe type your question or comment into the chat because the audio doesn't seem to be working. And in the meantime, Brad, do you want to comment?
Yeah, I think one of the aspects related to ground motion, and it's sort of the this area in between ground motion and source physics, is radiation of ground motion and how it relates to high frequencies, low frequencies, and we would learn a lot by this type of experiment for our rupture models. You know, we learned the Parkfield experiment, the UPSAR array was designed to capture this, and I think this experiment with clusters of stations would work very well. You don't want them right on top of the fault, you want them a little off the fault. I don't know what distance these clusters are going to be from the fault, but that's very important to capture the rupturing past and identify how coherent is the rupture front, how fast is it moving, where the radiation of high frequencies relative to low frequencies relative to the rupture front. Those are huge questions for ground motion modeling when it comes to generating ruptures. And we need these observations to be able to answer all those fundamental questions about how the rupture propagates and radiation of ground motion.
Can you hear me now?
Yes.
Okay, I changed the setting. And actually, Brad just made the point that I wanted to make. But I think one of the goals that we should have, it might not be achievable, is to be able to predict in the for the next like magnitude 7 earthquake, can we say anything about where the maximum slip might be for that earthquake and where maybe the patches along the fault that generate the high frequency ground motions would occur? Because it may depend on complexity, like Albert said. These things may be able to be discerned with some resolution before the earthquake occurs. And I think that would be a really lofty goal to do that. I mean, also it affects, the variability of ground motion for near field sources depending. What we see in a lot of earthquakes is that where the maximum slip occurs is not where the high frequency is generated. So it'd be really good to get out information about that. You might need some GPS information about where the fault's locked. You need to understand the structural complexity of the fault zone at depth. And I also agree with Brad that one thing it's not really the near fault observatory, but the one thing we really need are these aerial arrays located maybe 10 kilometers from the fault, so we can really figure out where the high frequencies are coming from along a fault when a big earthquake occurs. So I think this is a big hole in our current instrumentation around these faults. That's all. Thanks.
Norm?
Yeah, so following up on what Art just said, does it make sense to be doing, let's even call them your blind predictions, the data that you got from a few years of small magnitudes, and say, let's do predictions of a suite of sevens or something like that that you can compare. And as you start to get more data, you could update those predictions, but that gives you something to work on while you're waiting for the big event, and gives us some real tests, because we haven't had those before.
That would be great.
I think that'd be really good. I have proposed that we do that nationwide. I mean, we have recordings of small earthquakes, so a lot of fault zones, say New Madrid, South Carolina, Charleston, and California. We have the empirical Green's functions now. Yeah. Make some simulations of big earthquakes from it.
Shall we wrap up considering time? Okay. All right. Any final thoughts, Jamie, Gail?
Just basically thank everybody for your participation, and especially the speakers for leading us through some great discussions. I think there's going to be a lot to think about here. Jamie?
Yeah, that's all I was going to add, is thank you to everybody who joined in and commented. And if you have comments that you haven't yet put in the chat and you still want to get them, please email Gail and I, and we'll make sure that those comments get included in the notes.
So we don't have to put them in the chat, right? We can just send you an email. Is that right?
Sure.
Yes.
That's we can make sure, if you send it to us, we'll make sure it gets into the notes of the meeting. So
thank you.
That'd be great. Thanks.
All right, well, then also thank you to Jamie and Gail for organizing this, to Ken, Greg, Norm, Annemarie, and Albert for your presentations, and for everyone else for your participation in this session. The recording will be made available on the IRIS Earthquake Science playlist. If you're interested in future community near fault observatory breakout sessions and other events like tomorrow's, please check out the website in the link provided. And thank you so much for joining.
Thanks, everybody.